This was something we already had discussed, but again, as we work with algebraic geometry, we encounter singular varieties, and this is really important. So the typical example of singular variety is this union of two curves. You have xy equals 0. The important thing that you can actually decompose it into a union of two varieties, x equals 0 and y equals 0. They're both smooth. On the other hand, you might encounter this kind of singularity. Again, I forgot the formula for it. Maybe you remember? Well, anyway, this I do remember. It's x squared is equal to y third. This is the kind of singularity which you remove the singular point and it remains connected. This is not obvious that it remains connected, but you should think of that as of complex will work over C. So this, if you remove the singular point, this will be just a line, complex line without 2 points. It is connected. And these two cases are sufficiently different to be important. This distinction is important. Okay, so there's this definition of smooth points. It was there already. And so, well, I don't even need to write the definition. You probably remember it. But last time we discussed the inverse function theorem, which gives you a way of producing coordinates on a smooth manifold. Here's a proposition which is pretty much trivial, which says that these coordinates can be chosen polynomial. So because, so remark, if you have M smooth manifold, and then you have f1 dot fn functions, and n-dimensional. And you have n functions such that their differentials df1 dot dfn. You take the differentials in a point x, and this is a basis in cotangent space. So they're independent and generate the whole cotangent space. In that case, this coordinate system, f1, then f1 dot 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 fn, a coordinate system at the point at x in n. Okay. So if you have a smooth submanifold, which is just smooth as submanifold, you can take functions which generate its cotangent, the differentials generate cotangent space. Linear functions are okay. So locally, your submanifold is something like, it's approximated by linear submanifold. So you just take linear functions which generate, which are linearly dependent and generate its cotangent space to this submanifold. You can, it's not necessary to take linear. You can take some other ones. In fact, it's that the observation we can take linear function is slightly misleading because linear in, you embed your, you consider your algebraic variety as a subvariety in Cn. But there are different embeddings which give the same subvariety. And of course, linear functions in one embedding will be nonlinear in another. Also, you have, I mean, suppose if M is in C n plus m, where dimension of M is C. Oh, sorry, n. You have linear functions which give you coordinate functions. So you have coordinate functions f1 dot 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 fn coordinates on M. You can choose them linearly, but then there's fn plus 1 dot fn plus m, other linear functions. Functions on C n plus m. They can be expressed to these guys, but only algebraically. So they're not, I mean, typically they are solutions to some algebraic equations. So it's a bad idea to think, we say polynomial functions is actually very bad wording. I will switch from polynomial functions to regular functions soon enough because of this observation. I mean, in local coordinates, you can take polynomial functions. They're clearly polynomial on your, if the coordinates are polynomial, but there are other functions which are not polynomial. Like if you have things like quadratic, well, you can easily find the examples. So now I want to ask you, so do you know the analytic functions? Who knows analytic functions? So analytic functions are functions which are expressed as Taylor series. You can do real analytic, complex analytic, even periodic analytic makes sense. But you really need to have Taylor series, Taylor expansion of your functions. Not all functions have Taylor expansions. I mean, Taylor formally, of course, you can write the Taylor series, but it doesn't need to converge even in small neighborhood first. And second, even if it converges, it can converge to some other functions. In fact, there's a nice Olympiad type problem which you maybe have encountered, and they give you a formal power series, and you need to find smooth functions which have this power series as Taylor expansion. Of course, this power series can be very divergent. However, when you work with we work with regular functions. It's not hard to see that they remain they're even complex analytic. The easiest way is just to invoke the Cauchy theorem, which says that all complex differentiable functions are analytic. If you don't want to invoke Cauchy, you can remember that last time when I gave you the proof of inverse function theorem, it's easily works in analytic category. I mean, the whole proof, it doesn't care if you have Cn class, it will give you Cn diffeomorphism. C infinity, it will give you C infinity. Analytic, it will give you analytic. So these coordinates are really give you analytic coordinates, and all analytic functions, I mean all polynomial functions in these coordinates are analytic. With Cauchy it's easier. Do you have any questions? So now the main subject of today's lecture is irreducible subvarieties. This is these two cases of singularities. They can be distinguished, obviously. So definition, X is irreducible algebraic variety if X cannot be expressed as a union. X is equal to x1 union with x2 with x1, x2 algebraic, and x1 not inside x2, x2 not inside x1. It's like that. You have x, y equals 0. There's two lines, but it is union of two lines. Okay, so the first, do you know already about irreducible varieties? Who knows? Okay. The obvious claim is that, okay, so claim, suppose that A is affine, and OA is its regular functions, which are polynomial functions. Then A is irreducible if and only if OA has no zero divisors. This is a nice example when you can characterize geometric property algebraically, and this is equally important because sometimes you have to consider rings without zero divisors. In other cases, you have to consider irreducible varieties, and you can go from one to another. In fact, there's a whole chapter in I.T. MacDonald called primary ideals, which you have to avoid because they don't want to do geometrically, and what I will tell you today is the same as this primary decomposition that they give in I.T. MacDonald, and it's much easier with geometry. Okay, so proof. If A is A1 union with A2, both are algebraic, so there exists a function f such that f is equal 0 on A1 and f is non-equal 0 on A2. Otherwise, if such function doesn't exist, this means that vanishing on A1 implies vanishing on A2, but by Hilbert Nullstellensatz, ideal is determined by its zero set. So this would mean that, in fact, A1 contains A, if all functions which vanish on A1 vanish on A. So such function exists, and there exists G such that G is equal 0 on A2, G not equal 0 on A1. So this is in fact equivalent to non-irreducibility. So if you have such functions, you take their zero sets, this would decompose your A onto union of two subvarieties, zero set of F, zero set of G. Converse is also true. If you have decomposition, you have such F and G. Am I clear? Good. Yeah, but this is the same as zero divisors. So if you have, if F, G belongs to OA are zero divisors, F, G is equal 0, this implies that a zero set of F union with zero set of G is equal the whole A. And they are not zero by assumption, because they are functions on A. So you have zero. They have to be distinct, otherwise, They one cannot contain another because if this is contained in that, this is A. And then F is equal to 0. Am I clear? So this is obvious. It's not a complicated observation. Another observation is that proposition. Suppose that M is smooth affine manifold, affine variety, connected in topological sense. Connected means that it can be decomposed into a union of two open subsets. Then M is irreducible. Without connectedness, you can easily find irreducible smooth manifolds, smooth varieties. For instance, you can take a union of two lines. So x equals 0, z equal 1, y equals 0, z equal 2. This would give you in C3. This is a union of two algebraic varieties, so it has to be algebraic. On the other hand, it's two lines, which don't intersect. So this is a smooth, non-irreducible variety. Okay, so proof. Proof is based on what is called analytic continuation principle. Analytic continuation means that if you have a Taylor series for analytic function, it determines entirely on the whole domain if this domain is connected. So if you have an analytic function defined in some small open set, you can extend it to the whole thing. Well, maybe not, it can have some poles, so maybe the extension won't be possible, but it is definitely unique. Okay, so suppose it's not true. So suppose there exist Fg, which are zero divisors, such that Fg is equal to 0 and they're not 0. Okay, the important thing about Taylor series that they are formal, you can multiply formal power series. And if you have two non-zero power series, the product is definitely non-zero. So this means that for each point x inside our set A, there exists either f has or g has 0 Taylor expansion. Am I clear? Because if they have non-zero Taylor series, you can just multiply this power series, like you multiply polynomials. And product of two non-zero polynomials or power series is never 0. It's just formality. Okay, so let U be the set of all points where f has 0 Taylor expansion. This means that it has 0 derivatives. All derivatives are 0 expansion. Then U is open. Why? Because it's analytic. So if you have an analytic function, it has to be equal to its Taylor expansion and small neighborhood of each point. It is 0, so it has to be 0 in some small neighborhood, and closed because you have 0 sets for each derivative. It's closed. And then the set U is just the set where all the derivatives are 0, so it's union of closed sets. Okay, but the manifold is connected. if you have an open and closed subset of a connected manifold, it's either empty set on the whole M. And we are done, because this means that either F is 0 everywhere or G is 0 everywhere. Okay, converse is obviously non-true. Should remember this. Self-intersection. Okay, I can try to improvise, just to give you example. Or maybe I shouldn't. So I'm asking, what is the formula for this curve in C2? The curve which has self-intersection but is connected. It's something like, nobody remembers? Well, I should too. It's not hard to, but I don't want to think next to the blackboard. It's a good exercise for you. Anyway, the important thing that irreducibility doesn't imply smoothness, but smoothness implies irreducibility as long as your manifold is connected. Questions? Yes, please.
About that proof, did we regard M as a complex manifold and F and G as holomorphic functions in that manifold?
Yeah, it will work for the same reason. But I assume they're regular. It's stronger than holomorphic. Actually, restriction of polynomial.
When you use that either F or G as a zero-Taylor
Expansion, yes.
it means in the complex coordinate of the M?
Yeah.
In that sense?
Yeah. But you can take real coordinates. Doesn't matter. I mean, you can easily express real derivatives through complex derivatives and vice versa.
What do you mean analytic?
Yeah, analytic. So it's, of course, complex analytic is stronger than real analytic. But in fact, everything works with real. And if you can even do with what is called real algebraic variety, and this would be true, except that there are some real algebraic varieties, like you can have elliptic curve, which has this form. It's not connected, but it's irreducible. On complex, you will see that it never happens. Well, we shall discuss this. OK, so this is actually this corollary which I want to discuss. So corollary. Suppose that A is algebraic. A is smooth, so it's algebraic affine variety. And this smooth part, set of smooth points. I didn't prove that it is actually complement to an algebraic subset, but it is true. And suppose that it is connected. Suppose that A smooth is dense and connected. It's always dense, but I'm not proving that. It's sort of hard. It's not even true over characteristic P, so it's a complicated notion. So then A is irreducible. So this is a good criterion for irreducibility. So proof is easy. Suppose not. If this is false, not, you have there exists FG such that which are non-zero, but FG is equal 0. And then the same is true. Same is true on A smooth. In fact, since it's dense, they cannot be 0. I mean, if they are 0 on A smooth, then there is 0 everywhere. But this is impossible. By the previous resultants with this analytic continuation. And so this is a proof. And remark that this is actually equivalence, but I'm not going to prove that. It takes some complex analysis, non-trivial. So converse is also true. If over C, over reals it's false. Over C, connectedness, so irreducibility implies connectedness of smooth points. But at least this should give you some intuition how this thing works. So you can have like union of two varieties, you can separate them, or you can have something like that, which is singular but not separable. No, you can separate branches. Okay. Yeah, there is also exercise about morphism of affine manifolds. So image of irreducible is irreducible. Can you do that? So let me write the exercise, and I'm not going to have that because I'm not going to use it. It's a good exercise for you. You have f from x to g, to y, morphism. F of x is dense, and x is irreducible. Proof that y is irreducible. Can you do it? Anyone? Yes, please.
You say you take fg as functions in y, and you consider a 0 point because the image of x is dense.
Yeah. Then
The 0 point of f is closed and open. So when you pull back to x, it will be the 0 set in x when you compose with that f.
okay, what you probably say is that pre-image of a non-zero function is non-zero, right? Because of density. If it's
I mean, you use the same proof. If you have a f and g of functions in y, such that fg is 0,
yes,
and f and g is not identity 0 in y, then you get a function. If you compose with that map, you get a function fg.
yeah, but you have to use density.
Yeah,
Otherwise, it's false.
because open set, a non-zero open set, interject a dense set subset is non-empty. So they
Yeah.
work.
Yeah, very good. Thank you very much. Good. Okay. Now there's an extremely important concept of Noetherian rings. So who of you already had done Noetherian rings, or has heard about Noetherian rings? And who knows the the proof of Hilbert-Bayes theorem? Oh, that's very good. I was going to give it today, but then maybe I won't have time, and maybe, well, we shall have it later, in any case. So definition, Noetherian ring is a ring where any chain of ideals, you increasing chain of ideals like I0 sits in I1, sits in I2, sits and so on, stabilizes. So there could be only finite, non-trivial chain of ideals. If you try to do the converse, this will be false. So if you have I1 containing I2, containing I3, you can have infinite chains. Can you give me an example of infinite chain of decreasing ideals in like polynomial ring? Thanks. Precisely. So you have ideal generated by t squared, t third, and so on. This is decreasing chain of ideals. There are some rings which don't have decreasing chain of ideals. I mean, everything stabilized. They're called Artinian. And this is Noetherian. They are like dual properties. The important thing, of course, that all polynomial rings are Noetherian, or all the quotients of polynomial rings are Noetherian. So finally generated rings are Noetherian. This is Hilbert-Basic theorem. I will give its proof later, especially if I have time. Okay, so now about irreducible components. So definition: if you have a algebra affine variety, A is expressed as a union of A1 union with A2, and again A1 is not contained in A2, A2 is not contained, well, the second is not needed, and A1 is irreducible, then A1 is called irreducible component. This was the definition. And now the important result, which I'm going to prove, is that everything is a union of finitely many irreducible components. So this means that if you are really interested in geometry, you can restrict yourself to irreducible manifolds and then varieties, and then everything will be just union of some irreducible, finitely many irreducible subvarieties. So theorem, suppose that M is affine, then M is a union of AI, where all AI are irreducible components, and there are finitely many. So here I have this assumption, that, which is not needed, of course, because we know that affine varieties have finely generated rings, and they're rings of, so let's call it A, and OA is Noetherian. I don't need this assumption, and I will skip it because of Hilbert-Basic theorem. In fact, it's always Noetherian. Yeah. In fact, both statements are not entirely trivial. You have to prove both, so that it is a union and that are finitely many. Yeah, and however, if you have a decreasing infinite chain of algebraic varieties, so remark, this is the only thing I'm going to use from Noetherianity, that if OA is Noetherian, then any decreasing set, a chain of subvarieties, like A containing A1, containing A2, containing A3, stabilizes. This is clear because by Hilbert Nullstellensatz, subvarieties are the same as ideals. And so if you have a decreasing set of subvarieties, you have an increasing set of ideals. And this sequence, this chain of ideals, has to stabilize. But then the varieties has to stabilize because there's bijection between subvarieties and ideals such that the quotient has no nilpotent elements. Okay, questions? So at least something is clear from, we can have like, well, it should be already indicative of how you prove this theorem. You just use by absurd. Anyway. So let me now prove this theorem. So step one is existence of irreducible subvarieties. For each point A inside this big A, there exists irreducible component containing A. Okay, so suppose it's not true. So we can, this means that we can split A onto union of A1 union with A2, with A, say, in here. Or it's better to say A0, A1. And this will be again reducible because it can be a reducible component. So this will be equal to A0 union with A2 union with A1. Oh, sorry. No, it's bad numbering. So it's A, right, it's A1, A0. Here we would split A1 onto a union of two guys. So it will be like A0, A2, A3. No, it's very bad numeration. How to do it better? Okay, all right. I would do it like that. So it will be maybe it's, so it's A1 union with B1. But then A1 is also split. So this is the same as so we split A1 onto a union of A2 and B2. This is A1, union with B2. And A is in A2, because this is also non-irreducible. And then this is, by assumption, is also non-irreducible. So this is the same as A3, union with B3, union with B2, union with B1, and so on. And this is a decreasing chain of subvarieties, A1, A2, A3, and so on, which is impossible. So then we arrive at contradiction. So then there exists, so this, since it stabilizes, AI stabilizes, then the point A small is contained in AI, which is irreducible. You can't split it further because this would mean that you can extend indefinitely the decreasing chain of subvarieties or increasing chain of ideals. Okay, this gives you a union. So this, every point is contained an irreducible component. This means that A is a union of its irreducible components. So step 2. We obtained where AI are irreducible components. Okay. What we need now to show is that it is a finite union. This is step 3. Why it's finite? To see that, we again use the same sort of argument, which is slightly trickier because you have to, you have to we have some union which are not inside each other. So it's like a flower. You have lots of varieties, and you want to apply the this remark, you have to have a decreasing chain of subvarieties. So for that, I would use the terminology. So let's call algebraic closure of Z inside Cn is an intersection of all algebraic subvarieties containing Z. I want to mention that it is definitely algebraic subvariety, because what is a union of subvarieties? If you have, intersection. This is the same as ideal generated, its ideal is ideal generated by the first and the second. So, well, anyway, this is something we have discussed. Intersection of algebraic varieties is algebraic. Because to have an intersection, you just, so X, the ideal of X, so it's like annihilator of X intersected with annihilator of Y is the same we start with an ideal I, ideal J, and intersection of this annihilator is just annihilator of I plus J. So if you have this is given by the one set of equations, this is given by another set of equations, intersection given by the union of these equations. And if you have infinite intersection, just take infinite sum of ideals, and it is still an ideal. Could be, of course, empty, but then it is just ideal which contains one. Okay. So this makes sense, and we shall use this notion of algebraic closure a lot. In fact, it's a closure in what is called Zariski topology, where closed subsets are algebraic subsets. Now we take A union of AI. So, for instance, A1 union with the rest, AI. I bigger than 1. And let's call B, I is, so B1 is algebraic closure of A without A1. So B2 is a closure of A without A1 union with A2, and so on. So B1 Bi is contained in the union of the rest. So it doesn't contain some points in A1, some points in A2 for that reason. Otherwise, they won't be reducible, because the union of the rest is algebraic as well. So this is decreasing chain. B1 containing B2, containing B3, and so on. What we do, we just remove, there was this picture, many subvarieties. We remove one of them, we take the union of the rest, we take its closure, remove two, take the closure, and so on. This gives you a decreasing chain of subvarieties. Not a complicated business. So we arrived at contradiction. Okay, what I wanted also to tell you is that if you read I.T. MacDonald, there is this notion of primary decomposition. So primary ideal is precisely an ideal of reducible subvariety. And decomposition is decomposition of a subvarieties onto a union of reducible subvarieties. Okay, so let's have a break and we shall be back. And now I have a proper clock. So in 11:26, and we shall discuss Noetherian rings and Hilbert basis theorem. If you have any questions, feel free to ask now or anytime.
Professor, about that.
I could prove both, but it would be another course, because it would take like at least 4 or 5 lectures to do this. So what people do when they give a course on algebraic geometry, they just assume that. This, if you look on Mumford complex varieties, this is precisely what he does. Okay, we should continue. So Hilbert basis theorem. It's a nice exercise in commutative algebra. And if you had some bit of commutative algebra, you probably would be easy to digest this proof. Maybe you had already this proof, maybe you have different proof, but it's not hard anyway. So definition, finally generated ring is a quotient of polynomial ring of C or some field or even Z, T1 dot Tn. So these are generators, and then you have some relations, and the theorem, Hilbert basis, are finitely generated, then R is Noetherian. Again, you don't need it over C. You can do it over Z, over some other, any other Noetherian ring, in fact. So first, you notice that if you have a chain of ideals, so the scheme of the proof, if you have R quotient by I, and you have chain of ideals in R quotient by I, like I1 contained in I2, contained in I3, and so on. This gives you chain of ideals in R. You just take the map, let's call it pi, from R to R quotient by I, and you take pi minus 1 of I1 contained non-equally to pi minus 1 of I2, and so on. I mean, this is surjective map, so pre-image will give you another monotonous, strictly increasing chain. So this means that if you have a Noetherian ring, any quotient of Noetherian ring is Noetherian. So then if R is Noetherian, then R by I also. Okay, and here we have, so you can, if you have, so Hilbert-Basius theorem is just, in fact, it's a statement that if R is Noetherian, then R of t is also Noetherian. And then you use induction. So you add one variable, two variables, three variables, and each step you use this, and this implies that C of T1 dot Tn is Noetherian, and then this implies that a quotient also. Of course, you can put Z here because Z is Noetherian. It's easy because Z is principal ideal ring, and you can use. Okay. So what I'm going to prove is that just this implication. This is the only non-trivial part in the whole Hilbert-Basius theorem. Yeah. Yeah, so this is what is written there. Yeah, and there is an exercise for an example of a ring which is not Noetherian. It's not trivial, in fact. So do you know any rings which are not Noetherian? Good. You can take infinitely many variables. Another more practical example is ring of germs of analytic functions. So the formal series is Noetherian ring. But germs and, of course, polynomials are also Noetherian rings. But there's intermediate rings, which is analytic functions. Sorry, I'm wrong. Germs are OK, but analytic functions on disk are not Noetherian. Yeah, germs are Noetherian. Yeah, but then you can take ring of analytic functions on any, in fact, complex domain, like on a disk or C, and you can easily see that it is not Noetherian. This is a good exercise for you. Okay, so the idea how you prove that, you slightly expand the notion of ideals and you expand the notion of Noetherianity to models. This is one. Another, you do finally generated models, finally generated ideals, and you check that this is equivalent to Noetherianity. So definition. Do you know about models, in fact? Models over rings. So I will give a remark. So submodels. So R submodels in R are the same as ideals. Is this clear? So this is, if you know the, so what is a model? Model is a abelian group where your ring acts multiplicatively. It's like vector space, but over a ring. So here you just, submodel means that you can multiply by elements of your ring, and it remains in that. So because R times I inside I, this is a characterization of a submodel, and that the characterization of an ideal. Characterizes submodels and ideals. So definition, a model M over R is finitely generated if M is a quotient of Rn. You take nth power of R, this is a model, just like a free model, and you take its quotient by some submodel. In other words, this means that you have finitely many generators which generate this model. The same is for finitely generated ideals. It's just a special case of finitely generated models. So I is finitely generated if there exists A1 dot AN in this ideal I, such that each x inside I is expressed as x equal to some AI BI, where BI are elements of our ring. It's the same. You have finitely many generators, and everything is generated by these finitely many generators. Okay, the important thing about the finitely generated ideals is that if you have a chain which union is finitely generated, it stabilizes. So remark or claim. Suppose that I is finitely generated ideal in R, and I is a union of the chain where A0 is contained in A1, in I1, contained in I2, and so on. Then this chain stabilizes. The proof is easy. It's one line. You just take these generators. They have to be present in these ideals. Each of these generators is present in one of these ideals. So take the biggest one, which contains all of them. It generates I. So the idea is that you take In, which contains all AI, and then all these generators, and then In is equal I. Okay, so if we prove that all ideals are finitely generated, we are done. This is what we need to show. So corollary. Yes, and converse is also true, that if a ring is Noetherian, that all ideals are finitely generated. Just add one generator, add two generators, add three generators. So it would give you a chain of expanding ideals, which has to stabilize at some point. And when it stabilizes, it's precisely where the whole I is generated by your finitely many generators. So R is Noetherian if and only if all ideals are finitely generated. Am I clear so far? There's no questions, comments? It's all elementary. And okay. Yeah. So let's expand our notion to models. So definition, Noetherian model. Yeah, there is a definition of a model if you are interested. It's just a vector space, because we work over C, otherwise it would be a group, with algebra homomorphism to its endomorphism ring. Noetherian model. And of course, submodels are just subspaces which are preserved by this algebra action. Noetherian model is a model M over R such that for each increasing chain, M well, there is no, decreasing chain M1 contained in M2, contained and so on, contained in M, stabilizes. Of course, submodulus in the R is the same as ideal, so what we need to show is that R itself is a Noetherian model. Yeah, and there is a trivial remark. Submodels and quotient models of Noetherian are Noetherian. This should be clear, right? I mean, if you have a submodel, you have a chain inside, it gives you a chain in M. If you have a quotient model, you have a chain. You just take its preimage like we did with ideals. And this would give you a chain in your model. The important thing that if you have an this notion of finitely generated models, I already gave it to you. And model is Noetherian if and only if it's finitely generated. This is the same argument, in fact. Yeah, but it should be over Noetherian ring. Sorry, this exercise is slightly wrong. Anyway, ring is Noetherian if and only if it is Noetherian as an R model. It's essentially a tautology claim. R is Noetherian if and only if R is Noetherian as R model. There's nothing to prove. Because ideals are the same as R models, chain of ideals is the same as chain of submodels. Okay, so what we need to show is that if you have a model, so this is a trivial remark, if M is R of T model, which is Noetherian as R model, it's Noetherian as R of T model. Yeah. There's a certain corollary which I don't think there should be the proof of it. Maybe I have somehow missed it, but it's not hard. So if R is Noetherian, ring, then Rn, the free model, is Noetherian model. Use induction for that proof. We consider this Rn is mapped to R. Here we have Rn minus 1, 0, 0. Maybe it's in the next slide, but maybe I just forgot to add it. Okay, so you have a chain of submodels here. So it's Mi inside this. then you take its image there, it has to stabilize. So let's assume that it's already stabilized there. Then they are different only by pre-image here. But by induction, we can assume that it stabilizes there as well. And sorry, if I didn't explain what is exact sequence, it is a sequence of modules, vector spaces, where this is surjective, this is injective. So this is Rn is a quotient of Rn minus 1 by R. Oh, sorry, of R is a quotient of Rn by Rn minus 1. Okay. So we're almost there. I think this is just the last slide, and we're done. Yeah. So what I'm going to prove is that I will start with R of t. I will take an ideal, and I will okay, so let me do it properly. So you have, I will start with an ideal given by leading coefficients. The idea is, suppose you have an R containing a polynomial P of t, ideal I, which sits inside R of t. So this is an ideal in the polynomial ring. And suppose it contains a polynomial with leading coefficients, coefficient 1. Then I if you have an element in I, you can take its quotient by P of t. So what you have is you have principal ideal generated by P of t. This is free, map it to A, and this would be mapped to something finite because you can take a quotient. I mean, you can divide. You can use division with, and this gives you this kind of Rn. Yeah, because up to this polynomial with leading coefficients 1, any other polynomial is determined by its quotient. But of course, we don't have this luxury. We don't necessarily have all polynomials have any polynomials in our ideal with leading coefficient 1. We have to do something more complicated. So step 1, we take I0 inside R. This is so we have an ideal I inside R of t. We want to prove that it's finitely generated. We take I0 inside R, which is ideal generated by leading coefficients. Coefficients, which are the coefficients with the biggest power of t. And it's finitely generated by assumption. Finitely generated because R is Noetherian. And this is an ideal in R. So let's call it generators A1 generators of this ideal I0. And then you can have corresponding polynomials P1 of t dot Pn of t, corresponding polynomials. Okay. So step 2 is the maximum of the degrees. We take n as maximum of degrees of pin. And then for each polynomial with for each polynomial q of t in our ideal, there exists a product with degree of q bigger than n. There exists a polynomial which is a sum of ai bi, where bi, actually let's call it, how it's called here, qi, no. There exist polynomials, let's call it R, oh no, R is bad, VI. There exist polynomials of the form sum of AI, BI, PI, same leading coefficients. Right? So what we can do, we just express this leading term through, say, A as a sum of BI, AI, and then replace AI by the corresponding PI multiplied by T. So you have to multiply by T power degree of P, or n minus degree of Q, let's call it N1, N1 minus degree of P. So the leading term of Q is this, then you have this expression. Okay. Then Q is, you can do induction and obtain that Q is degree degree n polynomial up to an ideal generated by P1 dot Pn. Okay. Now we can consider a quotient of our ideal by these polynomials. This is so this was the step, well, I didn't count the steps, but this here it's step 4. Consider the model M, which is a quotient of the of I by the ideal generated by Pi. By the previous argument, this injects to Rn plus 1. Because each polynomial is comparable with degree n polynomial up to the ideal generated by Pi. And degree n polynomials are precisely Rn plus 1. So this is surjective. This is the map which takes from this element, for any element, it makes the corresponding Dn polynomial and just takes its coefficients. Okay, so this is a submodel here. It's Nestorian by assumption. It's finally generated. So we take generators of this M and add P1 dot Pn. This would give you generators of this ideal. So obtain that every ideal is finally generated. This gives you the Hilbert basis theorem. I did it slightly fast because almost everybody knew that. So if you have any questions, we can ask. But otherwise, I think I'm done. There's no time anyway. Do you have any questions, comments? Good. So we did the irreducible decomposition. And I think next time we shall have something like quotient maps. Well, we have to be able to produce new algebraic varieties from old ones. We can take subvarieties, but it's more fun to have something better. And there is a good construction.